Hello everyone, welcome to this challenge question walkthrough for Edexcel's Pure Year 2 textbook chapter 7. So for this first question from exercise 7a, we've got a triangle constructed from two right angle triangles T1 and T2, and for part A we want to find expressions for for the area of T1, T2 and the large triangle in terms of x, y, a and b. So it would be good to start by writing the sides in terms of x, y, a and b. So we can use that using SOHCAHTOA. So here this side length will be y sine b because it's opposite the angle b, and this one therefore y cos b. And very similarly down for T1 we've got x sine a and x cos a. So the area of T1 then is going to be a half times the base times the height, so half x squared sine a cos a. And then for part 2, for T2 it's going to be a half y squared sine b cos b. And then for the last part, the area of the large triangle, we're just going to add them together. So a half x squared sine a cos a plus a half y squared sine b cos b. Okay, then for part B, we're asked to prove that sine of a plus b equals sine a cos b plus cos a sine b, the compound angle formula for sine. Okay, so we know from part A that we're going to have to do something to do with areas, and it seems like a sensible idea to find the area of the large triangle because we've got the angles A and B here that make up one big angle A plus B. So yeah, we can work out the area of the larger triangle using a half AB sine C, because we've got these sides here A and B, and we've got the angle between those two sides A plus B. So that seems like a good idea. So we can say the area of the large triangle, which we already know is a half x squared sine A cos A plus a half y squared sine B cos B. That is equal to a half AB, or xy, sine of A plus B. And now to get sine of A plus B by itself, we can just divide both sides by a half xy. So well, actually, first of all, we can cancel out all of the halves to make our life a bit easier. So the first term then is going to be x squared over xy, or x over y, sine a cos a, plus, and then now it's going to be y over x, sine b cos b. Now at this point it looks like we're a little bit stuck, and there's no more information to help us out, but actually if we look back here at the original triangle, we can spot that y cos beta, or y cos b, is actually equal to x cos a. And that's useful here because now we can work out what x over y and y over x are to eliminate them from this equation. So we can figure out what x over y is. So that's going to be rearranging that cos b over cos a. And then we can do the same for y over x. That's going to be cos a over cos b as the reciprocal. Okay, so now we can replace the x over y and y over x with those expressions up there. And luckily things cancel out for us. So we can see we've got cos a in the denominator there and also multiplied here. So there you go. And then we've got cos a over cos b, and the cos b and the cos b in the denominator cancel too. So we end up with sine of a plus b, all in brackets, being equal to sine a cos b plus cos a sine b as required. Okay, now moving on to our first question from exercise 7f. We've got for part A, show that cos of a plus b minus cos of a minus b is equivalent to minus 2 sine a sine b. So here we can just use the compound formulae from this chapter. So cos of a plus b we know is cos a cos b minus sine a sine b. And then we know that cos of a minus b is then going to be cos of A cos B plus sine A sine B. Okay, and then we've got here cos A cos B, take away cos A cos B, they cancel. And then we've got minus sine A sine B and minus again sine A sine B, so minus 2 sine A sine B is our answer for part A. For part B, we want to show that cos P take away cos Q is equivalent to minus 2 sine of P plus Q over 2, a sine of P minus Q over 2. So again, we can notice the similarities between part A and part B, and it seems quite clear that we can get what we're looking for if we let P equal A plus B, and then Q as A minus B. So now we've defined what P and Q are here, we can work out what A and B are by solving these essentially simultaneous equations for A and B. So we can add them both together to get P plus Q is equal to 2A. And so we have A is equal to P plus Q over 2. We can take them both away. So equation 1 take away equation 2 will give us P take away Q is equal to, the A's cancel, B take away negative B is 2B. So we get that B is equal to P minus Q over 2. And then if we plug them back into the original identity, then we're going to have cos of A plus B, which we now know is P, or we've said is P. Take away cos of Q is equivalent to minus 2 sine of A, which is now P plus Q over 2, and then sine of B, which is P minus Q over 2, as required. And then finally for part C, we need to apply this to write 3 sine x sine of 7x as the difference of cosines. So we can use the identity again. So if we consider what we've got at the moment is minus 2 sine of P plus Q over 2 sine P minus Q over 2. If we want that to be 3, then we're going to multiply both sides of the identity by minus 3 halves. So we've got minus 3 halves cos P minus cos Q is equivalent to minus 3 halves times minus 2 gives us positive 3 sine of P plus Q over 2 sine of P minus Q over 2. Okay, so now the right hand side here looks identical to the what we want to express as a difference of cosines, apart from the fact that we now need to figure out what our P and Q are going to be. So if we want one of the sine terms to be sine x and the other one to be sine 7x, then we want P minus Q, then the smaller one, to be equal to x, and then P plus Q over 2 to be 7x, which gives us that P minus Q is equal to 2x and P plus Q is equal to 14x. And then doing the same sort of thing as we did before over here. If we label this equation 3 and equation 4, then adding them together gives us 2p is equal to 16x, so p is 8x. And then taking them away gives us 2q is equal to 12x, so q is going to be 6x. Okay, then all we need to do is plug in the values of p and q into the left hand side over here. So 3 sine of x, that one there is actually 7x. So 3 sine of 7x sine of x is the same thing as minus 3 halves cos of p, which we know is 8x. And then we're going to add on to that because we've got a double negative. 3 halves of cos of q, which is 6x. And then probably you want to rearrange this just to show it's definitely a difference. So it's 3 halves cos of 6x, take away 3 halves cos of 8x. And that is our answer. Okay, now for the second question, we've got, first of all, to prove that sine p plus sine q is equivalent to 2 sine of p plus q over 2 cos of p minus q over 2. So in this case, instead of using the cos identity, we're going to use a sine identity. So sine of p plus q, and we should use a and b in this case, is equal to sine of a cos of b plus sine of b cos of a. And then we have sine of a minus b being equal to sine of a cos of b take away sine of b cos of a. And then now we can add these together to eliminate the sine b cos a terms. So if we add equation 1 and equation 2 together here, we're going to have sine of a plus b plus sine of a minus b being equal to 2 sine a cos b. Now we just need to match it up to what we had before. So on the left hand side we've got p and q being equal to a plus b and then a minus b. Then we can solve for a and b, doing exactly the same thing as before. So let's label these 3 and 4. Equation 3 plus equation 4 gives us p plus q equals 2a. So a is p plus q over 2. And then similarly, if we take them away, we've got p take away q over 2 being equal to b. And putting them back into what we've got over here, this really identity, we can then get that sine of p plus sine of q is equivalent to 2 sine of, and then a is p plus q over 2 and b is p minus q over 2, and that gives us exactly what we require. Okay, for part B then, hence or otherwise show that 2 sine of 11 pi over 24 times cos of 5 pi over 24 is root 3 plus root 2 all over 2. So now we can set our p plus q over 2 to be equal to the bigger out of 11 pi over 24 and 5 pi over 24, and then p take away q over 2 is therefore going to be the 5 pi over 24. And again, we can solve these simultaneously without too much issue. So here, if we multiply by 2, we've got p plus q being 11 pi over 12, and here p minus q being 5 pi over 12. Adding them together and dividing by 2 gives us p is equal to 16 pi over 12, divided out by 2 is 8 pi over 12, which is the same as 2 pi over 3. And then q is going to be, if we take them away, so we have 11 pi, take away 5 pi is 6 pi over 12, or pi over 2. Divide that by 2 gives us pi over 4. So we can plug these values into the left-hand side here. So we know that 2 sine of 11 pi over 24 times cos of 5 pi over 24 is equal to, let's do it up here. So 2 sine of 11 pi over 24 cos of 5 pi over 24 is equal to sine of 2 pi over 3 plus sine of pi over 4. And using your exact values, sine of 2 pi over 3, if we look at the graph of sine, or your cast diagrams if you prefer, 2 pi over 3 is here. So reflecting that in the line x equals pi over 2 will give us the other value here on this side being pi over 3. So we know that sine of pi over 3 and sine of 2 pi over 3 are equal, and sine of pi over 3 we know is root 3 over 2. Or you can just plug it in your calculator if you prefer. And sine of pi over 4, we should know that that is root 2 over 2. Adding those together gives us the root 3 plus root 2 all over 2, as we were asked to prove. Okay, for this question from exercise 7G, we're told to look at the model over here. So the electric field strength E in the microwave width 25 centimeters can be modeled using this equation here, where x is the distance in centimeters from the left-hand edge of the microwave oven. And we're told for food of the same type and mass, the energy transferred by the oven is proportional. So energy transferred is proportional to the square of the electric field strength. And we're told that a square of chocolate placed at a point of maximum field strength takes 20 seconds to melt. And then part A asks us to estimate the range of locations within the oven that an identical square of chocolate will take longer than 30 seconds to melt. Okay, quite a lot of information there. Let's start with this relationship that we wrote down here. The energy transferred is proportional to the electric field strength squared. Now, really, this energy transferred thing is, or it should be energy transferred per second. So the energy transferred per second, just to give it like a time frame, so we know how long is the energy being transferred for, because obviously the energy transferred for 1 second is going to be different for the same microwave. Everything else is the same. So that's going to be different for 1 second as it is for an hour, obviously. So it's probably more precise to say the energy transferred per second, so the rate of energy transfer, or the power, is proportional to the electric field strength squared. Okay, we know that the energy transfer per second, or the power, is equal to the energy over time from GCSE physics or A-level physics. So we can see here that for a constant energy, so the amount of energy needed to melt that identical piece of chocolate is going to be the same. So the energy needed is constant. So we can say that the power is proportional to 1 over the time. And we can then put that into here. So this energy transfer per second is proportional to 1 over time, which is then proportional to E squared. So we can just say that 1 over T is proportional to E squared. Okay. From this point then, we can write an equation. So we can say that 1 over T is equal to K E squared. And then we can use our initial condition from that point. So we know that a square of chocolate placed at the point of maximum field strength takes 20 seconds to melt. So maximum field strength, looking at this equation that we were given at the top up here, maximum field strength is going to happen when sine of 4 pi x over 25 minus 0.6435, that term is equal to 1. So remember, sine goes between 1 and minus 1, so the maximum is going to happen when this whole term here is equal to 1. So the maximum electric field strength is going to be 1,700 plus 250 times 1, which is 1,950. Okay, so we know the maximum field strength, so we can plug that into this equation down here. So E squared is 1,950 squared. We're trying to find K, and the time is 20 seconds, so 1 over 20. Okay, so then we can rearrange to find K, which turns out to be 1 over 76,050,000. Okay, so now we need to think about how we're going to find the range of locations, so the range of X. Within the oven, that an identical square of chocolate would take longer than 30 seconds to melt. Well, if it actually does take 30 seconds to melt, then we can work out what the electric field strength would have to be. So from this equation here, we've got that E squared is equal to 1 over kT. So E is equal to the square root of 1 over kT. So what we can now do is find the electric field strength when T does actually equal 30. So this will be sort of like the threshold electric field strength, so we can call it ET. So this is going to be equal to the square root of 1 over K, which is 1 over 76,050,000, times by the time, which is 30 for the threshold. And this gives us 1,592.168, and this is in volts per meter. Now, if we want the range of X within the oven, so the range of distances within the oven, where it will take longer than 30 seconds to melt, then we want the electric field strength to be lower than 1,592.168. So if we return back to the original equation then, this one up here, then essentially we're trying to solve the inequality now. 1,700 plus 250 sine of, let's call this whole thing in there theta, just to speed things up a bit. So 1,700 plus 250 sine theta is going to be less than 1,592.168. And then we can rearrange a bit and find that the equation we need to solve is sine of theta is less than, so taking away 1,700 from both sides, dividing both sides by 250, gives us minus 0.4313. Okay, so we're now trying to solve the trigonometric inequality. Sine of theta is less than minus 0.4313. It would probably be a good start to figure out, okay, what's the interval we're looking to solve this inequality for. So we know that we're looking at a microwave of width 25 centimeters. So we've got 0 must be less than or equal to x, must be less than or equal to 25. Now, theta is 4 pi x over 25 minus 0.6435. So what I like to do when I'm solving these equations is to sort of tweak the range, or tweak the interval so that we have it where theta is in the middle, so we can figure out where we need to be looking for when we're solving sine of theta is less than minus 0.4313. So to do that, we can multiply all sides of this inequality by 4 pi over 25 and then take away 0.6435 from it. And what that will give us is, first of all, if we times by 4 pi over 25, then this side, the right hand side, is just 4 pi. Then we can take away 0.6435 and see that theta, which is this thing in the middle here, has to be between minus 0.6435 and 4 pi minus 0.6435. So this here, remember, is equal to theta. So now we know we're solving the equation sine of theta, or the inequality, sorry. Sine of theta is less than minus 0.4313 between these two limits. And 4 pi minus 0.635 is equal to 11.9228. So we can keep that in mind when we're accepting or rejecting solutions for this range later on. Okay, so because we're solving an inequality, and usually how I like to solve trigonometric equations anyway is to draw a graph. You can use class diagrams, but it might be a little bit trickier in this case. But I always like to use graphs anyway. So here is a graph of y equals sine of x, or y equals sine of theta. So we need to go from just past the y-axis on the left side to just before 4 pi. So I'll draw all the way to 4 pi. So 1 cycle, 2 cycles, and I'll adjust the axis there. There we go. And then also I'll go just to like minus pi over 2 there. Okay, so we can I'll label these bits as well. So that's 2 pi there, that's 4 pi there. And then we're saying this is minus pi over 2 at the end over here. So minus pi over 2. And I'll label the x-axis as well, just to reinforce the fact that this is for theta and not for x, just yet. Okay, first of all, to solve the inequality, we need to find where sine of theta actually equals minus 0.4313. So I'll draw that bit over there again, that was a bit poor. There we go. So minus 0.4313 is about there. Okay, ignore the slightly slanted line, but yeah, that would be good enough for our purposes. And we want to find all of these values where sine of theta equals minus 0.4313. So we can start by finding the inverse sine, the principal value from your calculator. So inverse sine of minus 0.4313 and so on gives minus 0.4459. So that's our first solution over there. Okay. Then we can use the symmetry of the graph to find the next one. If you spot that this distance here from the first solution to the y-axis is going to be the same as the distance from pi over here to the next solution, because of the symmetry about pi over 2. Or in this case, it's theta equals pi over 2. So yeah, this solution there is going to be then pi plus 0.4459 by the symmetry, and that gives us 3.5875 and so on. Okay, and the third solution then is going to be 2 pi on from the first solution. So 2 pi minus 0.4459 gives us 5.8372. Then this one here is going to be 2 pi on from the second solution. So 2 pi plus 3.587 gives us 9.8707. And then finally, this last solution is going to be 4 pi on from the first solution. So 4 pi minus 0.4459 gives us 12.1204. So all of these solutions are in the range that we're looking for, apart from the 12.12, which is greater than 11.9228. So we can cross that out. So we've got our 4 solutions for theta, which I'm circling in purple now. And we just need to convert them into solutions in x. So if we have theta being equal to 4 pi x over 25 minus 0.6435, we can rearrange to find x. So x is therefore going to be 25 over 4 pi lots of theta plus 0.6435. If you go about the process of rearranging there, make sure you include your brackets too. So we can use this formula and plug in each of the values of theta that I've circled in purple here, and then convert them into x values. So I like to use the table function on my calculator to do that. So then plugging these values of theta into that formula for x gives us that x is equal to 0.3929, 8.4174, 12.8929, and finally 20.9174. Okay, so the last thing we need to do now is to actually solve the inequality we were looking at earlier. So sine of theta is less than minus 0.4313 at all of the points I am highlighting now in light green. So from there to there and from here to here as well. And then if we match them to the solutions in x, we have, okay, well this region over here goes past the interval. So if minus 0.6435 from our interval from earlier is somewhere there, then we've gone past that interval, so we can start the inequalities for x from 0. So we've got 0 is less than or equal to x is less than 0.393 to 3 decimal points. Then the next section over here, the next one along, is going to be from the second solution to the third. So between 8.417 and 12.893, again to 3 decimal places. And then finally, we've got from the last solution, so 20.917, all the way to the end. So remember, the last solution was out of range, so the final point, the 11.9228 must be somewhere before the 4 pi, and so we're going right to the end of the range for x, which is 25. So the final range bit is from 20.917 all the way to 25. So those are the ranges of locations within the oven then where the chocolate will take longer than 30 seconds to melt. And all of those are in centimeters. Okay, and finally then, state 2 limitations of the model. Well, we can say that the model assumes that the electric field strength is the same no matter where we are in the microwave, as long as we're a distance away from the left edge. So for example, this point here and this point here are the same distance away from the left-hand edge of the microwave oven. But the model assumes that even though there are different positions in the microwave from front to back, that they have the same electric field or the same energy transferred by electric field strength. And also the microwave oven might not work exactly the same way every time it is used. So maybe there's fluctuations in power, etc. And for the mix exercise 7, the first question here has 2 parts, and we're given 2 identities to prove. So first of all, we have cos of 2 theta plus cos of 4 theta over sine of 2 theta minus sine of 4 theta is equivalent to minus cot theta. Okay, so as usual we start with the most complicated side and see what we can do. So let's start with cos of 4 theta. So cos of 4 theta we can write as 2 cos squared 2 theta minus 1. And then on the bottom, sine of 4 theta we can write as 2 sine 2 theta cos 2 theta, using the double angle formulae on top and bottom there. So that's the left hand side. Okay, and now we can do a little bit of work with the top. So this is really like a hidden quadratic in cos of 2 theta. So you can imagine this as being 2x squared plus x, take away 1, which you can factorize into two brackets as 2x minus 1, x plus 1. So on the top we're going to have 2 cos 2 theta minus 1 and cos of 2 theta plus 1 being multiplied together, all over sine of 2 theta multiplied by 1 minus 2 cos 2 theta. Now we can recognize that this 2 cos 2 theta minus 1 and this 1 minus 2 cos 2 theta are the same, but one is negated. So we can cancel them out and just stick a minus symbol out in front there. So we now have minus cos of 2 theta plus 1 over sine of 2 theta. And again, we can use the double angle formulae for the second time. So on top, we've got cos of 2 theta, which we can write as 2 cos squared theta minus 1 plus 1. So they will cancel. And then sine of 2 theta we know is 2 sine theta cos theta. So some more cancelling happens. 2 and 2 cancel on top and top. 1 cos theta from cos squared theta and the cos theta on the bottom. So luckily we're left with just minus cos theta over sine theta, which we know is minus cot theta, and we're done. Okay, now for part B then. Again, we can start with the left-hand side, and it looks sort of reminiscent of what we were doing earlier in an earlier question with the identity, which I'll write out here. So we had from earlier cos A plus cos B is equal to 2 cos of A plus B over 2 times cos of A minus B over 2. Now, if we look at what we've got on the left-hand side here and what's on the right-hand side, we can see that there's a cos 3x carried over. So maybe it's a good idea to leave the 2 cos 3x as it is for now. And then if we focus on the cos of x plus cos of 5x, if we have a look at what that gives us, so cos of x plus cos of 5x using that identity from earlier up here. So cos of x plus cos of 5x, if a is x and b is 5x, then we get that is equal to 2 times cos of 6x over 2, which is 3x, which is looking good, and then cos of a minus b over 2, which is cos of... Now, it doesn't really matter the order of a and b, because we can swap them around, because it's just adding cos of x and cos of 5x. We could have said it was cos of 5x plus cos of x. So we could say cos of, so x, take away 5x is minus 4x, divide that by 2 gives us minus 2x. But because cos is an even function, we can ignore the minus essentially. So that's the same as 2 cos of 3x times cos of 2x. Okay, so returning to the question then, we've got on the left hand side cos of x plus cos of 5 of x. We've got cos of x plus cos of 5x, which is 2 cos 3x cos 2x plus 2 cos 3x. And then we can factorize, so we can bring 2 cos of 3x up front, and then this gives us cos 2x plus 1, and then we can use the double angle formulae in reverse. So we know that cos of 2x is equal to 2 cos squared x take away 1. So cos of 2x plus 1 is therefore going to be equal to 2 cos squared x. So then rearranging, simplifying a little bit, gives us the answer that we were looking for. So that is equivalent to the right hand side, and again we're happy. Okay then, for this final question, question 2 from mixed exercise 7, we've got a circle here with the points A, B and C on its circumference. AC is the diameter of the circle, and point D lies on OC, such that ODB is 90 degrees, as shown there. And we're asked to use the construction to prove, first of all, that sine of 2 theta equals 2 sine theta cos theta, and then for part B, cos 2 theta equals 2 cos squared theta minus 1, the double angle formula that we all know and love. Okay, so first of all, we can use a little bit of geometry to figure out some angles because we've only got one angle here. However, we can say that the radii here mean that the triangle OAB is isosceles, so this angle here is also theta. And then we can say this angle here then is 180 minus 2 theta, and then this one here then has to be 2 theta. Okay, that's a good start. We also know that from circle theorems, if we've got AC being a diameter, then the angle ABC up here is going to be a right angle, as it's an angle subtended in a semicircle. Then that means that looking at the triangle ABC, we've got the angle ACB being 90 minus theta. And this angle here is obviously a right angle, so we can say that the angle CBD is going to be theta. Okay, that's very good. We've now got some angles we can work with. To prove that sine of 2 theta equals 2 sine theta cos theta, we're probably going to have to do something with the triangle OBD, where we've got 2 theta as an angle. So if I draw that out separately so it's clearer. So this is the triangle OBD, where we've got this angle here being 2 theta, a right angle here, and then we know that this side length OB is going to be 1 because it's a radius. Okay, so sine of 2 theta then is going to be the opposite over the adjacent. So sine of 2 theta is just going to be equal to BD. BD over 1 is just BD. So sine of 2 theta is BD, so we need to somehow work out what the length BD is. So to find BD, it might be a good idea to have a look at some other triangle that has BD as a side. So one of those examples, a right angle triangle, is ABD. So if I draw that out again here, so A down there, B up here, and D here. We've got a right angle. This angle here is theta. From this triangle then, we can write that sine of theta is equal to BD over AB. But we know that AB, we can look at the triangle ABC. So if I draw the triangle ABC out, just like we did the others, now I'll draw it in an orientation that is more familiar. So if I draw B down here, and then C up here and A across here, then angle BAC is theta. So BAC over here is theta. We know the length of AC because that is the diameter, so that would be 2. So we can say that the length AB then is 2 cos theta. So here we can replace AB with 2 cos theta. And then we have now a formula for BD. Multiplying both sides by 2 cos theta gives BD equals 2 sine theta cos theta. And because we already know that BD is sine 2 theta, we can then say that sine 2 theta equals 2 sine theta cos theta as required. So for part B then, if we return to the triangle ABD, then we now know AB has length 2 cos theta. And if we want to work out what cos of 2 theta is, we know that cos of 2 theta, if we look at the triangle OBD up here, then cos of 2 theta is the length OD. And the length AD is from A to O plus O to D, so that's 1 plus cos 2 theta. We know then that cos of theta is equal to the adjacent over the hypotenuse, so 1 plus cos 2 theta over 2 cos theta. Multiplying both sides by 2 cos theta gives 2 cos squared theta equals 1 plus cos 2 theta. And then finally, taking 1 from both sides, cos of 2 theta is equal to 2 cos squared theta, take away 1, as required. And that is the end of the challenge question walkthrough for Edexcel's Pure Year 2, Chapter 7. I hope you enjoyed this one. If you like the video and want to see more, then please do like and subscribe to the channel. But apart from that, thank you very much, and I'll see you in the next one.